Answer a more fundamental question. What is relativity? Relativity, fundamentally, is the study of how different observers view the same reality. For example, take a situation where one person is on a moving train and another person is standing outside the train. If the person inside the train throws a ball, the two people will give two different accounts of the same event. The person on the train will say that the ball was moving slower and traveled less distance than the person outside the train. Situations like this are very important in physics because they raise the question, which observer is correct? The short answer to this question is that they both are correct. We just have to be able to explain why their observations are different, hence the study of relativity. There are three main things in physics with the name relativity: Galilean relativity, special relativity, and general relativity. Galilean relativity was first described by none other than Galileo in 1632, where special and general relativity were both discovered by Einstein in 1905 and 1916 respectively. Most people will have heard of, though not necessarily have been taught, special and general relativity, but not many people have been exposed to Galilean relativity, or at least not explicitly. If you've ever taken an introductory physics class and talked about Newton's laws, you've used Galilean relativity. However, in this context, it is usually taken for granted since it can seem like common sense. Let's look at an example of how Galilean relativity works. Meet Isaac and Albert. Isaac and Albert are trying to get to the same all too exciting conference on physics and are both taking the train. Isaac arrives to the station on time and boards the train no problem. However, Albert was stuck in traffic and was late getting to the station. As Albert gets to the station, the train leaves with Isaac on board, stranding Albert at the station. Say the train is traveling at some velocity v relative to the train station. According to Isaac, the conference is getting nearer and nearer the longer he is on the train, while for poor Albert, the conference is staying the same distance away. The universe obviously isn't changing, but the two people experience very different realities. How can this be? You might say, Isaac is just moving and Albert is not, so of course the conference looks like it's getting closer to Isaac. And of course you'd be right. But how can we reconcile the two different observations of the same universe? This is actually surprisingly simple to do. Let's say that the distance Albert is from the conference is delta xa, and the distance Isaac is from the conference is delta xi. Since Albert is not moving, delta xa will not change, but since Isaac is moving, delta xi will be a function of time. Since Isaac started at the train station that Albert is stranded at, we know that when t is equal to 0, delta xi is equal to delta xa. This is a good start since we can see that there is already a relationship between the experiences of Isaac and Albert. Since the conference will be getting closer to Isaac at a steady rate, we know that delta xi should be a linear function of time, looking like delta xi is equal to mt plus b. We already know that b is equal to delta xa since this is Isaac's starting point, and we can guess that m is related to v since how quickly the conference approaches Isaac directly depends on how fast the train is moving. This relationship becomes clear when we realize that Isaac's distance to the conference is decreasing. This means that as time goes on, delta xi must get smaller, so we can confidently say that m is equal to negative v. Putting this all together gives delta xi is equal to delta xa minus v times t. This result is known as a Galilean transform, and it relates the different experiences of Isaac and Albert just like we wanted. We can also solve for delta xa and get the inverse Galilean transform. Delta xa is equal to delta xi plus v times t. What else do these equations say? Let's look at a different but similar situation. Now suppose Albert is floating around in space and Isaac is floating past Albert at a speed v. When Isaac passes Albert, he takes out a ball and throws it at speed ui according to Isaac. However, since Isaac is moving relative to Albert, Albert will see the ball traveling at a different speed, call it ua. How can we find a relationship between the two velocities ua and ui when our transformations only give us a relationship between observed distances? Well, we have to be a little tricky about it. We know that a distance traveled by a moving object is given by its velocity multiplied by the time it's been traveling. If you don't believe me, you can just look at the units. Velocity is distance per time, multiplied by time gives us distance. So we can rewrite delta xi as ui times t and delta xa as ua times t. We then plug these into the inverse transformation since we want to find out how fast the ball is moving according to Albert. This gives us ua times t is equal to ui times t plus v times t. Then we can cancel off the t in each term, and that gives ua is equal to ui plus v. This says that Albert sees the ball travel at the speed Isaac throws it plus the speed Isaac is moving relative to Albert. This is exactly what we would expect, so another point for Galilean relativity. If you notice, we only considered cases where Isaac's and Albert's frames of reference were moving with constant velocities and no accelerations. These frames of reference are known as inertial frames and are incredibly important in physics. This leads us to perhaps the most important result of Galilean relativity. Things always move the same way in any inertial frame. Try throwing a ball straight up in the air inside a moving car. As long as the car isn't accelerating, the ball will come right back down whether the car is standing still or speeding down a highway. This concept is called Galilean invariance because motion does not vary between inertial frames. The notions of Galilean invariance and inertial frames form the fundamentals for Newton's laws of motion and ultimately the entirety of Newtonian mechanics. Once we know these concepts, we can understand how a motor turns the wheels on your car, how to construct massive skyscrapers, and even how to launch rockets into space.